Welcome back. Let's let S be a set of elements of a group G. Then, um, the subgroup generated by S um, um, is the smallest subgroup of G containing S. So writing S within the inequality signs here denotes the subgroup generated by S. It is the smallest subgroup of G containing S. So there may be many subgroups of G that contain S, and this is the smallest one that contains S. If the operation of G is multiplication, then the subgroup generated by S is the set of all products of powers of elements of S. So the subgroup generated by S is the set of all products of powers of elements of S if the operation is denoted by multiplication. If the operation is denoted by addition, then the subgroup generated by S is the set of all sums of multiples of elements of S. Okay, so the reason is, if a subgroup contains S, obviously that subgroup will contain any product of powers of elements of S, right? Because a subgroup is closed under the operation, and so if you have a subgroup that contains S, then it must contain products of all all products of powers of elements of S. On the other hand, if you look at the collection of all such products, that's going to form a subgroup of G. So therefore the subgroup generated by S is this collection of all products of this form. And then similarly, I can make a statement for the additive notation. Here's an example. Let's say in the set of integers, what's generated by 8 and 14? Well, we have just learned here that under addition, the subgroup generated by S would be the set of all sums of multiples of elements of S, right? So we know that the subgroup generated by 8 and 14 is the collection of all sums of multiples of 8 and 14. So 8z is the collection of all multiples of 8. 14z is the collection of all multiples of 14. So this would be the collection of all sums of multiples of 8 and 14. And so that's what's generated by 8 and 14. Now we know the GCD of 8 and 14, which is 2, can be written as a linear combination of 8 and 14 by using the extended Euclidean algorithm. So the GCD is 2 for 18 and 14, and you can write 2 as 14 times -1 plus 8 times 2. Okay, so now I want to show that the subgroup generated by 8 and 14 is the same as the subgroup generated by 2 only. And recall that every subgroup of Z is cyclic, so the subgroup generated by 8 and 14 should also be cyclic. Now, okay, so first of all, I want to show that the 8Z plus 14Z is a subset of 2Z. How do I do that? Well, if I take any element of 8z plus 14z, well, that's going to be a sum of a multiple of 8 and a multiple of 14. But then so if I look at a sum of a multiple of 8 and 14, well, automatically that's multiple of 2, because 8 is a multiple of 2, 14 is a multiple of 2. So we have that every element of the set 8z plus 14z is a multiple of 2, so it belongs to 2z. So 8z plus 14z is a subset of 2z. On the other hand, notice that 2 is 14 times negative 1 plus 8 times 2. So if I look at any multiple of 2, then say 2n, then I can write 2n as 14 times negative n plus 8 times 2n. So I see that any multiple of 2 is a sum of multiples of 14 and 8. So as a result, we see that any multiple of n, any multiple of 2 is in the subgroup generated by 8 and 14. So the subgroup, so the set 2z is a subset of the set generated by 8 and 14. So we see that the subgroup generated by 8 and 14 is the same as the subgroup generated by 2. And so we have come up with a simpler description of this subgroup. In Z20, I would like you to check that. I would like you to find what's generated by 8 and 14. Basically, the answer should be that this subgroup is the same as the subgroup generated by 2 in Z20. So this is the subgroup generated by 2 in Z20. And that should be the same as the subgroup generated by 8 and 14. Okay, so a bunch of exercises here. Okay, so so this should be the set of complex numbers. So if I look at the set of complex numbers under addition, then what is generated by 1 and I? Well, you get the collection of all sums of multiples of 1 and I. So multiples of 1 would be just integers, and multiples of I would be n times I. So you're looking at all sums of the form m plus ni, where m and n are integers. What's generated by 2 pi and root 2 in R under addition? Well, you look at sums of multiples of these 3 elements. So you're looking at 2 times a plus b times pi plus c times root 2, where a, b, c are integers. Okay, so I'm going to stop the video here, and in the next video we will be talking about the center of a group, and also we will talk about centralizers.